Welcome back to the next video, everybody. Today we're going to be looking at Galois deformation conditions. So the idea is we're going to take a lot of the general theory we've learned about deformation problems and apply them to the situation we care about, which is Galois representations. So we're going to fix a coefficient ring lambda, a residual characteristic p, and a natural number n. We'll let k be a number field and s be a finite set of non-Archimedean primes of that number field, containing all primes of residual characteristic p. A global Galois deformation problem for the quadruple lambda n, k, and s just means that for each prime lambda and s, we'll specify a local deformation problem for the decomposition group pi, which is g sub k sub lambda, where k sub lambda is the completion of k at lambda. In the sense of the subsection or the video, if you like, on deformation conditions. So more explicitly, what does this mean? For each prime lambda and s, we'll specify a full subcategory d sub lambda fn lambda g sub k sub lambda and fn lambda g sub k sub lambda. Remember, this was like rank n representation spaces over lambda of the group g sub k sub lambda. And what will this subcategory satisfy? It'll satisfy the three major conditions from the beginning of the deformation conditions video. So there were three major conditions being closed under. Essentially, it's kind of like being closed under sub-objects, intersections, and direct sums. Okay. So, given such data, we'll define a full subcategory dfn lambda gks of fn lambda gks by restricting objects in big category AV such that when for each lambda and s, they're considered as objects of the local space fn lambda g sub k sub lambda, they actually lie in the subcategory d sub lambda fn lambda g sub k sub lambda. Okay, so basically you're saying like you're going to define a deformation problem locally for each prime in s, and then when you move up to the global space, you're just going to require that things, when you consider them as local deformation problems, restrict down to the correct subcategory you define for each prime in s. Okay, so a specific kind of global Galois deformation problem is a global Galois deformation problem with fixed determinant. This is a slight variant of the above. Given a character delta from GKS to lambda cross, we'll let dfn lambda GKS delta denote the full subcategory of dfn lambda GKS consisting of objects AV of determinant delta as per the last video. Okay, so proposition 23, if you give me a global Galois deformation problem, the full subcategory dfn lambda GKS and fn lambda GKS defines a deformation condition for GKS. The same is true given a global Galois deformation problem with fixed determinant delta for the full subcategory dfn lambda GKS delta and fn lambda GKS delta. And really the proof of this is just definitions. There's nothing too interesting going on here. Okay, this is basically kind of like the content of the last couple of videos. If you satisfy the three major conditions, then the corresponding space of representations will be a deformation condition. Okay, it follows that global Galois deformation problems with or without fixed determinant give us deformation conditions. Okay, well then it makes sense to ask for a description of their Zariski tangent A modules. Okay, and that'll give us some kind of cohomology to work with. So proposition 24, let's let D be the deformation condition attached to a global Galois deformation problem for GKS, and for each lambda and s, let's let D lambda be the corresponding local deformation problem. Let A be a coefficient lambda algebra, and let rho from GKS to GLN of A be a continuous homomorphism. So we have a representation, a Galois representation on our hands. We'll set V equal to V of rho, the representation space. Then there's a Zariski tangent A module. TD rho makes a Cartesian square of A modules in the way that you kind of expect it to. TD rho maps to H1, GKS, and V. It also maps down to the direct sum over lambda and S of the sub-cohomology groups H1D sub lambda of GK lambda and V. And those map into the direct sum over lambda and S of H1, GK lambda, and V, and this square commutes. So what are the maps? Well, the horizontal homomorphisms are the natural injections, basically coming from the content of the video on the cohomological interpretation of Zariski tangent A modules. Okay, I mean, these guys just live in here basically by definition of H1D lambda, and then TD rho will live in here by the video I just referenced. How about the vertical maps? The right-hand vertical homomorphism is just restriction of cohomology, right? And then the point is there's a map here that commutes the square. That's the idea. Okay.
Hey, you got your letter?
Yeah.
Yeah, I love mine.
So I was recording a video, by the way.
Oh, I'm
Yeah.
sorry.
Yeah. Yeah, I did just get the letter. Welcome back to the next video, everybody. Today, we're going to be looking at Galois deformation conditions. The idea is we're going to apply some of the general theory we've learned about deformation problems to the Galois representation situation. So fix a coefficient ring lambda of residual characteristic P and a natural number N. We'll let K be a number field and S be a finite set of non-Archimedean primes of K containing all primes of residual characteristic P. A global Galois deformation problem for the quadruple lambda NKS means that for each prime lambda NS, we'll specify a local deformation problem for the decomposition group pi, which is just notation for G sub K sub lambda, where K sub lambda is the completion of K at lambda, in the sense of the video on deformation conditions. So more explicitly, we'll specify for each lambda and S a full subcategory D lambda Fn in Fn. Remember, Fn lambda GK lambda is like rank n representations over lambda of the group GK lambda. What will this full subcategory be doing for us? It'll satisfy the three major conditions from the beginning of the deformation conditions video previously. Okay. So closed under like direct sums, quotients, and subobjects. Okay. So given such data, we'll define a full subcategory DFN of lambda GKS. So now we're working kind of globally here of Fn lambda GKS by restricting objects AV in the latter, such that when for each lambda and S, you consider them as objects of this guy so locally. So Fn lambda GK lambda, they actually lie in the subcategory D lambda Fn that we just talked about defining, okay? So a global Galois deformation problem with fixed determinants is just a slight variant of this. For a character delta from GKS to lambda cross, we'll let DFN lambda GKS delta denote the full subcategory of DFN lambda GKS consisting of objects A comma V of determinant delta. I believe we talked about this in the previous video, what this actually means. Okay, but it sort of means what you think it means. Okay, so proposition 23, given a global Galois deformation problem, the full subcategory DFN lambda GKS in Fn lambda GKS does define a deformation condition for GKS. The same is true given a global Galois deformation problem with fixed determinant delta for the full subcategory DFN lambda GKS delta in Fn lambda GKS delta. And really, this is just definitions. This is just sort of true by construction and by results from the previous video on subcategories satisfying those three major conditions. Okay, it follows that global Galois deformation problems with or without fixed determinant give us deformation conditions. Well, great. So then we can ask about a description of their Zariski tangent A modules, and we can get some cohomology involved, right? So proposition 24, we'll let D be the deformation condition attached to a global Galois deformation problem for GKS, and for each lambda NS, we'll let D lambda be the corresponding local deformation problem. We'll let A be a coefficient lambda algebra, and we'll let rho from GKS to GLN of A be a continuous homomorphism, so a representation of GKS. We'll set V equal to V of rho, the representation space. Then the Zariski tangent A module TD rho does make a Cartesian square of A modules in the way that you kind of think it should. So you have kind of horizontal homomorphisms from TD rho to H1 of GKS and V, and from the direct sum over lambda NS of H1D lambda, subcohomology group, of GK lambda NV to the direct sum over the same lambda NS of H1 GK lambda of NV. So these horizontal maps just come from, they're natural injections coming from the content of the video on the cohomological interpretation of Zariski tangent A modules. So, well, this is just kind of definitions, right? Like H1D lambda lives in H1 by definition of H1D lambda. So I guess really it's this homomorphism here that comes from the video that I'm referencing. And then like the right hand vertical homomorphism is just induced by restriction on cohomology. And the point is there's a map here commuting these like you think there probably should be. Okay, so this TD rho kind of maps into the direct sum of all the like sub cohomology groups representing representing the local deformation problems. Okay, how about for fixed determinant? So proposition 25, let D be the deformation condition attached to a global Galois deformation problem with fixed determinant for GKS. So we're specifying a little bit more here. Then there is a Cartesian square of A modules like you think there's going to be. I won't detail the square out again. I'll just say it's the same as the above square, but you replace NV by NV circle. So trace zero endomorphisms because we've already shown in a previous video that that's kind of the cohomology you want to consider when you're working with Deformation problems with fixed determinant. You want to look at trace zero endomorphisms when you're looking at cohomology there. So this is no big surprise either. Okay, in fact, the proof is just previous video stuff. And basically, it's basically this plus previous video stuff. Okay, so let's phrase things in a different way. The Cartesianness of the first square above is equivalent to the following description of the sub A module H1 sub D GKS NB in H1 GKS NB. So proposition 24 prime under the setup of proposition 24 H1D GKS NB. So kind of the cohomology group related to that deformation condition consists of those cohomology classes in the full H1 GKS NB, which when you strict them locally to G sub K sub lambda, land in the submodule H1 sub D sub lambda of G sub K sub lambda NB in the full H1 for each lambda NS. I mean, this is just like not really saying anything, right? This is just saying that square above is Cartesian, right? We can, and also this is just kind of obvious, like you certainly hope this is true, right? I won't go through it, but you can produce a proposition 25 prime in the same way by looking at the Cartesianness of the second square above. So by looking at deformation conditions involving fixed determinant. Okay, so finally, so proposition 26, what if you have an absolutely irreducible residual representation so that you have like universal deformation rings at your disposal, etc.? Well, under the hypotheses of proposition 23, assume additionally that rho bar, of which rho is a lift, is absolutely irreducible. Then there are natural A module isomorphisms that you sort of expect if you've been paying attention to previous videos from A maps from the space of differentials lambda of RD over A, where RD is the universal deformation ring of the deformation problem D, completed tensor product over R sub D of A to A. So we have A maps kind of like out of the differential module to A. That should be isomorphic to TD rho, and that should be isomorphic to H1 sub D of GKS and AB. This is not new information, right? There's not even a proof required here. This is just old propositions and results applied to our specific setup, essentially. Okay, and then there's a similar statement, which is a variant of proposition 25, when in addition, we're looking at lifts of fixed determinant. Okay, so we'll keep pressing forward next video, continuing to apply what we've learned to the Galois deformation problem setup, and we'll be quickly wrapping the chapter up shortly thereafter. So I'll see you then, and thanks for watching.